Hi, everyone. Thank you for joining us today. I'm pleased to present. Our presenter is Robbie Pickering. Robbie Pickering is an environmental engineer with more than 13 years of experience promoting water efficiency
So single pass cooling, if present, has the potential to be the single greatest water waster in a facility. When looking for savings opportunities, this is a really good place to start. So single pass cooling is a situation where city water is plumbed to a piece of equipment to remove heat. This is typically a motor or a compressor. After the water goes through, it goes right down the drain. In a commercial facility, you might find this associated with an air conditioning unit, a walk-in freezer or refrigerator, ice machines, vacuum pumps, or medical equipment. This cooling method can use 40 times more water to remove the same heat load as a cooling tower. So you can see why it's important to get rid of. If possible, as I said, just get rid of it. You can do this by either replacing water-cooled equipment with air-cooled equipment, or by providing cooling water from an existing chilled water loop. There are typically significant cost and water savings available for these changes. In cases where you can't eliminate single pass water use, make sure that your system is using the absolute minimum volume needed. Check the equipment specifications and make sure that you're getting the temperature rise in the water that you're applying. Also make sure that the water turns off when the motor or the compressor isn't running. This is often controlled by a solenoid valve so that it activates or it shuts the valve when the motor or the compressor is no longer running. But in some cases, this valve can fail and it allows the water to flow at all times. So this is something, a maintenance item that's worth checking up on and that often needs attention. In some cases, single pass cooling water can be collected and reused for another purpose, but it really is just best to eliminate it before its use. These photos illustrate the potential magnitude of savings opportunity, particularly in setups that have a continuous flow of water. On the left, we have a flow of 1 gallon per minute, which would consume more than 500,000 gallons of water per year and cost about $5,600 at average water and sewer costs. And then at the right, you can see the flow equivalent of a garden hose at full flow. If that flows 24/7, it would amount to more than 3 million gallons of water use and cost more than $33,000 a year. So fortunately, most facilities that have substantial cooling loads use recirculated chilled water systems. Chilled water systems typically have several key components. They have a heat exchange unit. These are supplied with chilled water that are providing either space cooling or in some other equipment cooling. This is where the heat load comes from. The chilled water takes that heat load and directs it back to the chiller. Typically, chilled water loop is a full closed loop, and therefore you should be seeing very little water loss or consumption in this chilled water loop. It's good practice to have makeup water meters on the chilled water loop so that if you see any consumption or continuous makeup, you can identify that you likely have a leak and you can get it resolved. So the chiller unit is what generates the chilled water through a refrigeration process. The chiller transfers heat from the chilled water loop to the condenser water loop, which heats the water. And then lastly, the condenser on the refrigeration cycle may be either air-cooled or water-cooled. Larger units tend to be water-cooled using a cooling tower, as shown here. Water is evaporated from the cooling tower. We're not as concerned with air-cooled models from a water efficiency perspective, so we're going to get into more detail on cooling towers now. That condenser unit or cooling tower then cools the water and returns it to the chiller. So that we have everyone oriented on cooling towers, I just want to take a moment to go over some of the basics. The concept is fairly simple. Water and air flow past each other, typically in a counter current or cross flow configuration. In this schematic illustration, hot water from the chiller is introduced at the top of the tower by spray nozzles, and they flow down along a fill material while air is drawn up through the tower by a fan. As the air passes over the water, some water is evaporated, which removes heat and reduces the temperature of the water in the tower. The energy lost via water evaporation helps remove heat from the system, and then this cooled water is then returned to the chiller to collect more heat. So the cooling tower has a number of inputs and outputs that help explain how water is being consumed in the system. So first, there's, as I mentioned, this circulated cooling water loop that is introduced into the tower to be cooled. The water is removing heat from a piece of equipment and is then returned to, in this case, a chiller, and it returned to the chiller once it's been cooled in the cooling tower. Some of this water is evaporated to remove heat. This is by design and is the purpose of the cooling tower. Some small quantity of water is often lost via small water droplets that spray from the tower. This is called drift. Some water is discharged as blowdown to keep minerals from building up in the recirculating cooled water loop. The cooling tower water loop or the condenser water loop. And then makeup water is added to balance the losses due to evaporation, drift, and blowdown. And we'll talk about each of these in a little bit more detail now. So now that we understand what's going into the tower and what's maybe leaving the cooling tower, we can understand where there are opportunities to save water. So there's a few options. We can either reduce the evaporation heat load on the cooling tower. We can reduce drift losses, reduce system blowdown. We can minimize the propensity for leaks, which are really just another form of unintentional blowdown. And then we can provide makeup water from a source other than city water. So because evaporation is the primary function of a cooling tower and how most of the heat is carried away, this really isn't the focus of our water efficiency efforts. Based on the thermodynamic properties of water, 1.5 gallons of water per hour are needed to be evaporated for every ton of cooling that is offered. So, and this number is fixed. So you're always going to use 1.5 gallons per hour per ton. Since we want that cooling to occur, we're not trying to limit evaporation at all. That being said, anything that you can do to make your chiller plant more energy efficient will also lower your cooling load and thereby reduce the amount of water needed for evaporation. So aspects of your facility that may impact your evaporation load include building design and envelope, HVAC design and equipment selection, lighting and plug loads, occupancy, operating characteristics, and maintenance practices. So for example, a lighting retrofit or system efficiency upgrade or really any other energy efficiency project can have a commensurate water savings as well from your cooling tower. So beyond water that is evaporated, some water can also be lost to drift or splash out. In a well-designed tower equipped with drift eliminators, this should really be minimal. However, if you're near your tower and you're noticing visible droplets that are exiting or kind of pooling of water outside, this may be a sign that your drift eliminators need some attention. Drift eliminators can be added to an existing tower. You can also get higher efficiency drift eliminators to replace older, poor-performing ones. They also have ancillary benefits as well, such as helping to reduce risk from Legionella or cooling tower water being sprayed in the outside environment. The other maintenance item to be aware of is the cooling tower overflow. Most towers are equipped with an overflow drain that prevents it from being overfilled in the event of equipment malfunction. If the level sensor or a fill valve or makeup valve in the tower fails, this can cause an overflow to the drain without the facility staff realizing it immediately. So the tower on the slide, or the photo on the slide, is of a tower basin where the fill valve controlling the makeup water was stuck partially open. Water was constantly flowing, overfilling the basin and going down the drain. This is a good thing to really monitor during daily rounds. A broken fill or float valve in a cooling tower can easily waste hundreds of thousands of gallons every day, especially if they go unnoticed. So it's definitely something to check in on. And in short, you should never ever see water flowing to the overflow drain. This is only meant for overflow situations. So if you see water in your overflow drain, check it out and identify the issue and correct it as quickly as you can. So the primary opportunity to improve water efficiency of a cooling tower is really in reducing the amount of blowdown by concentrating minerals in the recirculating system. For background, as the mineral concentration rises in the tower, the blowdown stream will discharge a certain amount of water and replace it with city water, thus reducing the overall concentration of minerals in the system. So mineral control and blowdown is necessary to protect the cooling tower and chiller equipment and to prevent the formation of scale, corrosion, or biological growth. A measure of this efficiency is called cycles of concentration, which is really the ratio of the concentration of minerals in the blowdown to the concentration of minerals in the makeup water. It's also representative of the ratio of makeup volume to blowdown volume. So the higher the cycles you get, the less blowdown is occurring. So if you recall our schematic from the cooling tower, the only water that's being added to the system is from makeup water. When operating properly, the only significant ways water is leaving the system is through evaporation and blowdown. The drift should really be negligible. So reducing the cooling tower blowdown, as I mentioned, is the biggest opportunity for savings. The reason for this is the blowdown is to keep minerals or dissolved solids from building up in the recirculated water throughout the tower. An example of that is shown here. So city water contains dissolved solids. As water evaporates, these dissolved solids stay in circulation and begin to get concentrated over time. If the concentration gets too high, the solids will begin to form scale buildup on the surfaces of the chiller system, which can degrade performance and damage equipment. There's some water that is regularly discharged. This is the blowdown to keep these dissolved solids in check. The blowdown is typically controlled by a conductivity meter or a controller. Careful blowdown control, as I said, offers really the best opportunity for savings in a cooling tower system. So this background establishes the basis for saying that by maximizing your cycles of concentration and reducing the blowdown, your system efficiency will improve. To maintain high cycles of concentration, you can keep minerals in solution by managing the system water chemistry. Minerals are kept in solution by adding chemicals or another treatment mechanism that can control the pH and inhibit scale and corrosion. The target cycles of concentration that is achievable in your cooling tower is based primarily on your facility's incoming water incoming water quality. This table is from ASHRAE 189.1, which establishes maximum values for certain parameters that recirculating cooling water should stay below. This information can be helpful in identifying your cycles of concentration limit. So, for example, if your limiting parameter is total dissolved solids or TDS, you can identify your target cycles by evaluating incoming water quality. If your incoming water quality's TDS is 1,000 ppm, your tower may only really be able to safely run at 2 cycles because 2,050 divided by 1,000 is approximately 2. However, if your incoming water has a TDS of 200, you might be able to achieve 10 cycles of concentration. So calculating that target cycles of concentration and establishing a water treatment program may sound complicated, and it can be. Oftentimes it is complicated. That's why most buildings commonly contract this out to a water treatment vendor. This is someone who comes on site or comes to your facility once every couple of weeks or months and checks up on the water treatment program. They'll take some measurements, they'll monitor chemicals, and make sure that everything is in working order. So when working with a vendor, there are some important things to keep in mind at the onset and throughout your relationship to ensure that you're achieving your goals. First, communicate your goals with respect to water efficiency. We encourage you to work with a qualified water treatment vendor that shares your goal of water efficiency and is willing to work with you to establish a target cycles of concentration based on your local water chemistry and the water treatment options that they're offering. Second, ensure that they're providing you with a comprehensive summary of their service visits. This should include water chemistry information. Your treatment vendor should be taking regular samples of your incoming water quality and the cooling tower water quality to help determine whether the goals that you established are being met. And if they're not providing this information, make sure to ask them to. Third, be sure that you're reviewing the service reports that they provide to make sure that they're achieving the cycles of concentration goals that you've both established together. So sometimes there's very valid reasons why these target cycles aren't being met, such as a mechanical failure. However, sometimes it's just a result of them not paying attention and not doing exactly what you hired them to do. So be sure to request these reports and review them regularly to make sure that they're meeting your goals. And then lastly, You should also try to find a vendor who can really be a partner in your water efficiency. Oftentimes, treatment vendors can be a resource for providing ideas or technology options or cost estimates for increasing cycles of concentration beyond what is achievable with typical chemical treatment. So this is an excerpt from a pretty typical water treatment report. The format of these reports can kind of differ a little bit depending on the vendor, but the information is usually the same. And often the more information you get, the better. So the report includes conductivity on the makeup water and the cooling tower water. This cooling tower water is the same as the blowdown water that gets sent to the sewer. Dividing the blowdown conductivity by the makeup conductivity gives us a little over 6 cycles, which really isn't that bad. One other thing to be aware of, where does your conductivity sit with respect to the control point? So you can see on the right, the control point is 2,750. And in this case, the conductivity of the tower is at 2,755. So right at this upper limit, which is where you want it to be. In terms of retrofits that you can do to get the most efficiency out of your tower, first is to install an automatic controller that controls blowdown based on conductivity to maximize your cycles. You can also install makeup and blowdown meters to track your water use on an ongoing basis and monitor trends, taking corrective action if necessary. I mentioned this earlier, but one important cost-saving measure is that with appropriate submetering, some utilities will let you deduct the quantity of water you evaporate from your sewer bill. So these savings can be quite significant because cooling towers are big water users. So the cost savings from a sewer deduction can often be used to offset the upfront costs of installing meters or by installing other control mechanisms. So taking steps to improve water quality, such as side stream filtration or basin cleaning to remove sediment, can also offer efficiency improvements. In addition, water softening, if water hardness is a problem in your area, can allow you to increase your cycles of concentration. Your treatment vendor can often advise you on these types of options. So this chart on the slide shows the type of savings that you can achieve by increasing your cycles of concentration. So you read the initial concentrations on the left across the new cycles on the top. And so, for example, by improving from 3 cycles to 6 cycles would provide a 20% savings in cooling tower water use. And this chart here shows just a water consumption of a theoretical 100-ton tower at various cycles of concentration. And you can see by the shape that as you get higher cycles, there's this flattening of the curve since a greater portion of the water is being evaporated rather than blown down. So as you can see, this threshold point's around 5 or 6. So it's a good target to try to achieve 6 or greater cycles. And everything beyond that is kind of gravy. So I just covered a ton of information and best practices in a short amount of time. So I just wanted to take a minute and summarize some of the common failure points that could lead to water waste or cooling tower damage. As far as mechanical issues, you can have a stuck makeup or blowdown valve. A makeup valve that is stuck open will continually fill and overflow the tower. A blowdown valve that is stuck open will continually drain water, essentially creating a single pass system that also wastes cooling tower chemicals. A blowdown valve that is stuck closed will not be able to remove minerals from the system at all and could actually eventually lead to a scale event. Faulty sensors can have similar repercussions. If the conductivity or the level sensor isn't communicating correctly with the controller or blowdown valve, you could be blowing down too much or too little. Like any system, there's a potential for pumps to fail or pipes to leak. And then lastly, controllers, either for conductivity or a chemical feed system, can malfunction and again result in the tower blowing down too often or not enough. On the operational side, there's common failures include establishing incorrect set points at which the system should be blown down. Similarly, the level sensor in a tower could be installed incorrectly, leading to the tower underfilling or overfilling. The chemical feed system can be programmed incorrectly to apply too much or too few chemicals. The those are just a few examples. And most of these things can be pretty easily identified and resolved just by making sure that staff is assigned responsibility for the cooling tower and understands the basics of what's going on in the system. They don't necessarily need to be a mechanical engineer to know what to look for during regular check-ins or regular daily rounds. They should check the overflow drain to make sure water isn't flowing. They should monitor and record meter readings and use them to calculate cycles of concentration. And they should look at the conductivity meter to make sure the tower is operating at its set point. If they do these three things on a daily basis, you can really understand and identify when something is going wrong so they can be resolved before it wastes a significant amount of water and costs you a lot of money. So another opportunity to reduce the amount of potable water used in a cooling tower is to identify an alternative source of water that could be used to supplement or fully replace city water in the makeup line. Some possible sources of makeup water include reclaimed wastewater that's often provided by your local municipality, rainwater, foundational drain water, and air conditioner condensate. One thing to remember when assessing alternative water sources is that the water quality, quantity, and availability should be considered. So only use alternative sources when you're able to match the quality of the alternative source to the needs of the system. In that vein, air handler condensate can be a really excellent source of makeup water for a cooling tower, particularly if the facility is located in a hot, humid climate. Condensate is water that forms on air handler coils, cooling coils as it heats and conditions outside air. The condensate is typically drained right to the sewer or a storm sewer, but since it's generated in its highest quantity when the load on your cooling tower is also at its highest, it makes an excellent source of cold, clean water. The biggest challenge with this type of project is the plumbing required to get water from the air handler condensate line to the cooling tower. However, if the pipe runs are not too long or complicated, you don't need to make too many wall intrusions, that can make the project very cost effective. There's a few example designs that have been incorporated in some of the facilities that I'm familiar with. As you can see, these projects don't really need to be that complex or complicated. They can just involve something to catch the water, a submersible pump to pump it away, and the piping to get to the cooling tower basin. The Federal Energy Management Program, or FEMP, has created a really nice resource to help facility managers determine the potential for condensate capture. As you can see, facilities in the Southeast, Midwest, Mid-Atlantic, they all have really high potential for collecting condensate for these types of projects. That being said, really cost-effective projects can be available anywhere, provided that your air handlers are in close proximity to cooling towers. FEMP also has some really nice maps for rainwater potential, as well as reclaimed wastewater availability, which are two other potential sources of cooling tower. And just to kind of summarize, these are a few facilities I'm familiar with that implemented improvement projects, kind of running a range of different things, some collecting air handler condensate, some improving blowdown control, some finding alternative sources of water like RO concentrate, installing water softening, improving the cycles of concentration. You can see the scale of water savings that can be achieved by looking at your cooling tower and by addressing some of their inefficiencies. So the last mechanical system that we're going to focus on is boiler and steam systems. There are two main types of boilers. There are hot water boilers and steam boilers. Hot water boilers are either open systems, which produce hot water for domestic consumption or laundry operations, or they're a recirculating closed loop system that's used for space heating. Domestic hot water efficiency is mainly related to the efficiency at the point of use. So installing high efficiency faucets, shower heads, laundry systems, or cooking equipment will save water and energy. Recirculating closed hot water systems for space heating, similar to with the chilled water system, they should have very little makeup water demand. So again, you can install a meter just to make sure that you're not losing any water in that closed loop system. But the focus for our purposes for water efficiency is on steam boilers. So this is a very simple boiler sketch to orient everyone. Steam is produced in the boiler and used for either space heating or potentially other uses. Once the steam gives up its heat, it condenses back to water and is often collected and returned to the boiler. Similar to cooling towers, over time, minerals can build up in the boiler, and periodic blowdown is required to remove them from the system. Where this does vary from cooling towers is that this blowdown is really hot. And frequently, it requires a tempering water stream that is mixed with the blowdown to reduce the temperature below 140 degrees Fahrenheit, so it can be discharged to the sewer. And this is based on local codes. So makeup water is then provided to the makeup to make up for steam losses and the boiler blowdown. The most important feature of an efficient steam boiler system is capturing that steam condensate and returning it to the boiler. The water savings are threefold. First, you're returning this high quality hot water to the system, which both reduces the water use and the energy demand on the boiler system. It also eliminates the need for tempering water to cool the condensate before it's discharged. And lastly, it reduces the frequency of blowdown, since the condensate is high quality water with low mineral concentration. Steam condensate recovery as a result has energy savings. Since the steam condensate is really hot, it requires less energy to reheat and produce steam again, and much less energy than incoming city water that is, usually at, let's say, between 55 and 65 degrees. Aside from installation of a condensate recovery system, the key to an efficient boiler operation is to keep all the components in good working order. You'll want to check steam and condensate, steam and water lines for leaks, and check to make sure that steam traps are functioning properly. You'll want to regularly clean and inspect the boiler water and fire tubes for good heat transfer and tune up the boiler for efficient firing. Make sure steam lines and condensate return lines are properly insulated to prevent heat losses. One area that deserves careful attention and where we frequently see water savings opportunity is with the tempering water application. So tempering water is often applied where the hot condensate or blowdown is discharged to the drain. This could be on a boiler blowdown flash tank or condensate draining from a flash tank on a steam vent. These tempering water flows are frequently controlled by a temperature actuated solenoid valve. If the temperature probe or the valve fails, the tempering water can flow all the time, even when it's not needed. So as we saw earlier, any continuous flow of water can be a big water waster. So, make sure you're monitoring this valve on a periodic basis to make sure that it's only applying tempering water when blowdown or condensate is being drained. Alternatively, rather than using tempering water, sometimes you can use an expansion tank or a heat exchanger to cool the hot condensate or the hot blowdown before it is discharged. So this can be another opportunity. And in some cases, you can even reuse this heat from the heat exchanger to preheat some of the boiler makeup. So some concepts presented earlier for cooling towers also apply to steam boilers. You'll want to install and read makeup and blowdown meters. You want to maximize your cycles of concentration by capturing as much steam condensate as possible and by minimizing blowdown. And then again, work with a qualified water treatment vendor that is specialized in water efficiency to help you maximize your cycles while still preventing scaling or corrosion within your boiler system. By working with someone who knows what they're doing, this should reduce the amount of water use, your chemical use, and your overall costs. So WaterSense has developed many technical tools and resources to help with conducting a water assessment, creating a water balance, or otherwise understanding water use and water efficiency opportunities within different building types and within different systems. So cooling towers and mechanical systems are one of those. We keep all of our resources for cooling for commercial facilities on our commercial tools and training section of the WaterSense website. This section of the website houses technical guidebooks, assessment tools, worksheets, checklists, case studies, and links to recorded and other upcoming live trainings. So WaterSense at Work presents our most comprehensive guidebook and provides the most in-depth information regarding a lot of the systems we cover today. This guidebook is really meant to help facilities understand, manage, and reduce their water use. It includes best management practices covering water management planning, water use monitoring. It also has information on specific best management practices for different water uses. So sanitary fixtures, commercial kitchen equipment, outdoor water use, mechanical systems, laboratory and medical equipment. It also has some calculations that can help you estimate water use and water savings from certain projects. And we're in the process of updating many sections of this guide. So some of those updated sections are on our website already, and stay tuned for some more that are coming in the next couple of months. As I mentioned earlier, this is part of a monthly webinar series. Next month's topic is Energy Water Nexus, where we will discuss the energy that's embedded in water and ways that you can save both water and energy in your facility. You can register using the link on the slide. Then in December, we'll be talking about water metering and submetering, which can be powerful tools to understand and save water. In case you've missed any of our previous webinars, you can also find those recordings here as well. In terms of other resources, there's two that I want to point out. First, there's a tool from the Environmental Defense Fund that is called the Water Management Application, or Water Map tool. This is an Excel-based spreadsheet that has three primary components. There's a water scorecard, a water efficiency calculator, and a cycles of concentration estimator. The scorecard helps facilities or companies assess their water efficiency, and then the calculator estimates the water and financial savings from cooling tower upgrades or from implementing free air cooling. We didn't talk much today about free air cooling, but this is a concept of using outside air that is at low temperatures to assist with cooling loads. Using free cooling can reduce your facility's energy and water use. And then finally, the cycles of concentration estimator takes information about your water quality and estimates the recommended maximum cycles of concentration for your cooling tower. So we talked a little bit about that earlier, of how to calculate your target cycles. This is a tool that can help do that for you. Another great resource that is available is from the General Services Administration through their Green Proving Grounds. The GSA, obviously a big property owner, they evaluated a number of alternative water treatment technologies for cooling towers to try to validate vendors' claims on savings, efficiency, and other benefits. GSA summarized their findings in a detailed report. I think they looked at 4 or 5 systems, and some of them have really significant potential to reduce blowdown and increase cycles of concentration. So I look to this as a really great independent source on kind of validating some of those claims and looking for some unique opportunities to improve the water efficiency of your tower. So to kind of summarize, we covered a lot of ground today. So I just want to kind of go through some things you can do right now to get started in making your mechanical and HVAC systems more water efficient. First, check that any single pass cooling equipment is set to use the minimum flow rate required for cooling in all instances, and start investigating alternatives to replace these single pass systems. Install and read meters on all your makeup water lines to your cooling towers, boilers, and chilled water loops. Install blowdown water lines on your cooling towers and boilers. And also, if you have a condenser return system, you can install a meter there as well. Create a daily punch list or rounds checklist for assigned staff to monitor the overflow drain meters and cycles of concentration to make sure that the cooling tower is operating correctly. As I mentioned, doing these 3 things can really prevent a lot of water waste that occurs from a malfunction or mechanical issue that arises. Next, contact your utilities to see if they have any programs that could help you save water and money. This includes the sewer deduction credits, rebates, or assessment support. Take a minute to review the water chemistry reports that are generated by your water treatment vendor. to understand what your current cycles concentration is, and if your target cycles can maybe be adjusted. If your water chemistry allows, work with your vendor to increase your cooling tower cycles, targeting that 5 or 6 threshold. And then lastly, just take a look at the configuration of your facility to see if you can, if there's an easy way to route condensate from your air handlers back to the cooling tower as makeup water. Again, this can be a really pretty simple and cost-effective way to minimize the amount of potable water you're using. With that, I'm gonna open it up for questions. If you have any looking for additional information or questions about either Energy Star or the WaterSense programs, you can reach out to the contact information on the screen, and someone will be able to assist in answering your inquiry.
Awesome. Thank you so much, Robbie. This is a whole wealth of information. We have a bunch of questions, so I'm going to get to as many as I can in the time we have left. And if we don't get to yours, we'll email you with an answer. Are there recommendations from WaterSense for how often submeters should be calibrated?
That's a good question. What I've usually heard, I don't know that I have a specific recommendation, but usually the manufacturer literature from the actual metering manufacturer will provide you with the required calibration frequencies. Sometimes that can be a year, sometimes that can be 10 years, sometimes that can be, that these meters are forever calibrated. So I would look back at your manufacturer literature or instructions that are provided with those meters, and see what they recommend.
Okay. Are cooling towers economical for replacing a small single pass cooler? How small should be considered?
I would first look into installing an air-cooled model. Cooling towers are really good for providing a lot of cooling. Often they're cooling towers are installed to reduce the energy demand on facilities, and people are often focused on energy. But if it's a small, a small system, or I would just look towards an air-cooled model first. You might be surprised that the energy penalty, I'm using quotations, that you get from using an air-cooled model isn't as significant as you might think. And with water prices going up and up, you'll find that compared to a single pass system, that an air-cooled system can be very cost-effective.
Okay. What does a drift eliminator look like, and how much do they generally cost?
So they look like it's kind of like a grating. So it's like a grate, or I wish I should include an image of this in the future. They essentially they come in these plastic or metal sheets or panels, and they kind of snap onto the outside of the tower. And so, you can retrofit them. Most towers these days come with them already equipped. They kind of go on just the outside of the tower, and look very similar to the fill material as well. The one thing to look for with the drift eliminators is that if you see any big gaps, or if it's hanging outside or has rusted through, those are signs that you should replace them. As far as how much they cost, I think it varies depending on manufacturers, the quantity, the quality of them. But yeah, I don't really have much more information beyond that.
I think you covered this, but someone asked, can you talk about what kind of maintenance and operating routines we can adapt after we've done all of the water and energy efficiency upgrades? For example, what would routine checks include?
Yeah, so I kind of touched on the big three. This is something else that I'll steal from Anaki's webinar of you should never, a valve will always fail you. So if your makeup valve might be working today, but tomorrow it might get stuck open and waste hundreds of thousands of gallons. So monitor that overflow drain as frequently as possible. I've been at facilities where you see the overflow occurring, and by the time you catch it, it is literally hundreds of thousands of gallons. These are big pipes that flow to these towers to fill up the water. So yeah, first and foremost, monitor that overflow drain either visually or auditorily, or you can also sometimes install like a sensor or alarm in the overflow to notify you or your BAS system if overflow is occurring. So that's the first one. Make sure that your connectivity controller set point is accurate, or that your tower is operating at that set point. Oftentimes you can look on the connectivity controller and you'll see the set points at, let's say, 2000, but the tower is operating at 1000. And that's a sign that maybe a blowdown valve is stuck open, or some other issue is occurring. A sensor might be malfunctioning. The third thing that I mentioned was monitoring your meter readings. So whether that's daily or weekly, take makeup and blowdown readings and use those readings to kind of compare what the cycles you're achieving is to what you're expecting it to be. So if you're making up 5 times more than your blowdown, that's a cycles of 5. If that's what your set point is, great, you're all set. But if your cycles are actually 3 when you're expecting 5, again, that's an indication of a larger problem that you'll need to investigate. So I would say those are the 3 primary routines that you should adopt to make sure that your tower's operating efficiently.
Thank you. And I've heard that sometimes you can look at the size of the pipe if you're trying to determine which one's the overflow versus a makeup line. Is the overflow the bigger one?
Correct.
Generally?
So if you're looking at the cooling tower basin, there's sometimes confusion of what's the overflow versus what's the blowdown. 99.9 times out of 100, the overflow will be the bigger tube because it's meant to handle those catastrophic events where your tower is overflowing. The blowdown will be a smaller pipe. So look for the bigger pipe and make sure that there's no water leaving it. And if there is, certainly worth investigating further.
Okay, where can we find a qualified water treatment vendor?
So it depends regionally, obviously, but I'll say there is a organization, the Association for Water Technologists, which I think is like the primary training and certification for treatment vendors. I think they might have an online listing, so I would look into them. It's AWT or Association for Water Technologists. They might have a listing of where their certified professionals are, and I think that's a good place to start.
Okay. Let's see. Generally speaking, as it relates to a building owner's bottom line, how do water savings compare to waste and energy savings? Is one more dominant or popular than the other?
I'll just give my opinion here. I think historically, energy is the primary focus. Even today, within the federal government, there's a huge push on energy and decarbonization. And water can sometimes fall by the wayside. I think that equation has to do with what your local energy costs are. For you as a facility manager, or you as someone who's helping a building become more efficient, I think you'll need to make the determination of where to focus your efforts. Water costs and sewer costs are much more expensive now than they were 15 years ago. The balance of which is more expensive. Energy prices have stayed relatively consistent or have kind of kept up with inflation, whereas water's much higher. So, your focus or your attention might steer more towards water as costs for you become more and more. Again, that's kind of just my opinion, but I generally see that people focus more on energy, partially because that's what people better understand.
Okay, I think that's all the time we have for today. Thank you so much, Robbie, and thank you all for joining us. We got through all the questions, so hopefully everybody's got a good understanding at this point. And I encourage you all to join us for next month's webinar on the Water Energy Nexus in action, and check out the links for the slides when we send them out. and we'll also send you the recording. So thank you so much for joining us today. I'm going to wrap things up. Have a great rest of your day. Thank you.
Thank you so much, everyone.